So, hello, student. In the last class, we have discussed about the elasticity chapter, about its Hooke's law, various modulus of elasticity, and we also discuss about the some question, some short answer question and long answer question. Okay. Now, our next question is describe the behavior. Our next question is describe the behavior of a wire, the behavior of a wire under gradual increase of load, under gradually increasing load. But this topic also came in somewhat like that. Prove the this question also came like that. To prove define stress strain curve. Define stress strain curve. Defines stress strain curve. Both questions are same. Both have the same answer. Okay. Now, what are the answer? Just a minute. The condition. Suppose a body, suppose a body of length L is here. If I hang a load on it, so what will happen? The length of the body, the length of the body will increases. It will increase continuously till a point is came, which is known as the elastic limit. After that, a permanent set or yield point is come. After that, a breaking point is came. Okay, so we can study this in the form of graph. Now, firstly, when the load is increased in step, when the load is increased in steps, when the load is increased in steps, a graph is drawn. A graph is drawn between stress on the y-axis and corresponding strain on x-axis and corresponding strain on x-axis. Strain on x-axis. Now I'm drawing the graph between stress and strain curve. So in y-axis, stress is denoted, and in y and in x-axis, strain is denoted. Okay. Now, firstly, the proportional limit. First topic is your proportional limit. Proportional limit. So, what is the proportional limit? So, in the linear position, OA, stress is proportional to strain. Stress is proportional. Stress is proportional to strain. That means Hooke's law is obeyed by the wire. Is obeyed by the wire up to point A. Up to point A. Okay. So at point A, Hooke's law is obeyed. After the point A, Hooke's law is obeyed means at point A, if we remove the weight, so it will regain its original shape and size. Okay. So this point is known as the proportional limit. So whenever the stretching force is removed, whenever the stretching force is removed, the wire regains its original length. The wire regains its original length. Okay. So A is called the proportional limit. So A is called the proportional limit. A is called the proportional limit. Second point is elastic point. Second is elastic point. So what is the elastic point? If we increase continuously load, so what will happen? It will come at a point B. Suppose this is the point B at where Hooke's law doesn't obey. Means if we move the load from here, so it does not regain its original position. Okay, so this point is known as the elastic point. Means the maximum value of elasticity. Okay, this point is known as the elastic point. So in the graph, B is the elastic limit. In the graph, B is the elastic limit. Through the wire, So the wire doesn't obey Hooke's law. Doesn't obey Hooke's law. Okay. The wire regain its shape. Its original length after the removal of deforming force. Original length after the removal of deforming force. So what is the elastic point? If we continuously increase the load, a point is came where the stress is where stress is not directly proportional to strain. So that point is known as the elastic point. However, if we remove the load from it, so it will regain its original shape. Okay. Now next point is elastic point is end. Now next is permanent set or yield point. Permanent set or yield point. Mark this point important because it came in a single question also. Okay, what is permanent set or what is yield point? So if we increase load again, so a point will become C, which also does not obey Hooke's law. But of what happened to this point, if we remove a load from here, so it does not regain its original shape and size. It will come at this point. Okay, so C is a point in the graph. C is the yield point. If the stretching force, if the stretching force at C is removed, the wire doesn't regain its original shape, doesn't regains its original length, regain its original length, and the length of the wire changes permanently. And the length of the wire changes permanently. Now, after point C, if we continuously increase the load, so what will happen? The wire became thinner and thinner, and a point was came where the wire will break. So this point is known as a breaking point or a fracture point. So D is breaking point or fracture point. Now, last option is D. Breaking point, breaking point or fracture point. So what is this breaking point or fracture point? When the stress, when the stress increased, the wire become thinner and thinner. The wire becomes thinner and thinner, thinner and thinner when the stress when the stress increases to a certain limit, the wire breaks. The wire breaks. The stress at which the wire breaks is called breaking stress, and the point D is called fracture point. And the point D is called the fracture point. Okay, so that was your chapter. All we have discussed about the elasticity, the what is elasticity, what is the rigid body, what is deforming force, and next we have discussed in this chapter perfect elastic body, plastic body, perfectly elastic body, perfectly plastic body. Next is formula of stress, formula of strain, types of stress, tensile stress, compressible stress, hydrostatic stress, tangential stress. Next, we have discussed about the tangential stress. Next, we have discussed about the strain. Next, we have discussed about the type of strain, volume, longitudinal strain, volumetric strain. Next, we have discussed about the Hooke's law, modulus of elasticity, types of modulus of elasticity, its unit, and lastly, we have discussed about the compressibility and compressibility Poisson ratio and elastic potential energy. Now, in after that, I have discussed some important question which will come in your which had came in your previous year question. So these are very short answer question. These are long answer question. Okay. Now the important part from it is firstly, the stress sustain curve. Next, the elastic potential energy. Third one is types of modulus of elasticity. So at least you have to practice all these questions. Very short answer question, long answer question, and okay. So there will be a no numerical in this chapter, which had came in your previous year question. Okay. So firstly, you have to prepare all this question. So that's all in this chapter. Now I am coming to the chapter which I have left, thermodynamics. So in thermodynamic class, we are discussing the second law of thermodynamics. The second law of thermodynamics stated whether the reaction will be spontaneous or non-spontaneous. So so in second law of thermodynamics, there are two statements. First is Calvin Planck statement, and second is Clausius statement. Calvin Planck statement state that it is impossible to construct an engine which will produce no effect other than extracting heat from a reservoir and performing an equivalent amount of work. Or simply, you can say that Calvin Planck statement says to us that it is impossible to construct an engine whose sole purpose is to convert all heat energy to work. Now, next we have discussed in this the Clausius statement. The Clausius statement, in this statement, we have discussed one more point that all work done can be converted to heat, but all heat cannot be converted to work done. Okay. Now we have discussed in this chapter the Clausius statement. The Clausius statement says that the heat flows from hot body to cold body unaided, but it cannot flow from cold body to hot body without any external work. So means that we know that the heat flow due to the temperature difference. Temperature difference means the heat will be flow from high temperature to low temperature. That means heat will flow from cold body to hot body. If we want to flow the heat from hot body to cold body, so we have to done some external work. This is the clause's statement. Okay. Now next is to see that whether the heat engine counts or not in your previous year. There will be no heat engine, no refrigerator. Now the last is types of processes. There are two types of processes. First is reversible process, and second one is irreversible process. So process. There are two type of process. First is reversible process, and second one is irreversible process. Irreversible process. So what is the reversible process? A reversible process is a process means which can reverse in its opposite direction. Okay, but irreversible process cannot be reversed in its opposite in its original direction. That means example are rusting of iron, dissolve of soap in a water, all are the irreversible process. And the reversible process are melting point and boiling point, slow compression and expansion of elastic spring. So, firstly, we have to discuss the reversible process. Reversible process. So, what is the reversible process? A reversible process is one. A reversible process is one which can be retraced which can be retraced in the reverse order and in opposite sense, so that it passes exactly through the same state as in the direct process. Direct process. Okay. So example are slow compression and expansion, slow compression and expansion of elastic spring. Of elastic spring. Next example is melting and boiling point. Melting and boiling point. Okay. But the condition for reversible process is condition for reversible process condition for reversible process. So there are two conditions for reversible process. First is all steps all steps must be slow. And second one is loss of heat due to friction should be absent. Now next is irreversible process. Next process is irreversible process. So any process which cannot be retraced, which cannot be retraced in the reverse direction, which cannot be retraced in the reverse direction is called irreversible process. Is called irreversible process. So example of irreversible process are rusting of iron, and second example is dissolve of soap in water. Dissolve of soap in water. So that are your processes. Any other thing is left, so nothing will be left. Okay. One process or there, this is quasi-static process. Quasi-static process are infinitely slow process, so that in the system, thermal and chemical equilibrium, such that the system will be in thermal and in a chemical equilibrium with the surrounding. That process are known as the quasi-static process, but that are not important for your exam point of view. Okay, so I am not writing that process. Simply, you can remember the process in which the system and the surrounding are both in thermal and in a chemical equilibrium with each other. So that type of process is known as your quasi-static process. Now I'm discussing the previous year questions of the thermodynamics. Now, firstly, I am discussing the very short answer type questions. Very short answer type question. Now, first question is define calorie and what is the relation between calorie and mechanical equivalent of a heat. What is calorie? What is the relation between what is the relation between calorie and mechanical equivalent of heat? Mechanical equivalent of heat. So, firstly, define the calorie. Calorie is a unit of heat. So, it is defined to be the amount of heat required to be the amount of heat required to raise the temperature of 1 gram of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Or you can say that 1 gram of water to 1 degree Celsius. Okay, you can simply write it as 1 gram of water to 1 degree Celsius. So the correct definition of calorie is A, or you can simply write as the unit of heat is known as calorie. Next is mechanical equivalent of heat. One more topic is there, the one more mechanical equivalent of a heat. So what is this mechanical equivalent of heat? We know that all work can be converted into heat. Okay, the more will we work, so more heat will be produced. So work is directly proportional to the heat. After removing the constant of proportionality, after removing the constant of proportionality, a constant has came which is known as J. This J is known as the mechanical equivalent of heat. So J is equal to W upon Q. So the relation between the calorie and the joule is 1 calorie equal to 4186 joule per kg per Kelvin. So this is the value of 1 calorie. This is a relation of calorie between. This is a relation between calorie and mechanical equivalent of heat. Now, next question is what thermodynamic variable? What thermodynamic? What thermodynamic variables can be defined by can be defined by first is zeroth law and second is first law. Zeroth law and second is first law. So we know that the zero law state that if a body A and B are in thermal equilibrium with each other, and body A and C are in thermal equilibrium with each other, then B and C are in thermal equilibrium with each other. So what thermodynamic variable can be defined by zeroth law? So zeroth law can define a thermal equilibrium. Now, what's first law defined? First law defined as the heat supplied to the system is equal to work done plus internal energy of the system. So we know prior to this the heat we know, work done we know, but in this chapter we must this law is also based on the law of conservation of energy or law of conservation of energy that energy can neither be created nor be destroyed. Only it can be transferred from one form to another form. So first law defined by define internal energy, or you can simply say that the energy. Now next question is define state variable and the equation of state. Next question is define state variable and equation of state. So state variable are pressure, volume, temperature, mass, pressure, volume, temperature, mass, internal energy. These are known as the state variable. Means all the macroscopic properties of a matter is known as the state variable. And equation of and the equation of state is the connection between all these values are known as the equation of state. So firstly, what are the state variable? The state of a system which determine the pressure, volume, temperature, mass, and internal energy of the system is known as the state variable. And equation of state determine the relation between these state variables. Next question is what why a heat engine with 100% efficiency can never be released in practice. Next is why heat engine with 100% efficiency with 100% efficiency can never be released in practice. Can never be released in practice. So, firstly, I will give you a short revision about the heat engine. So, heat engine is a device which can convert work done into the heat energy. Okay, heat energy into mechanical energy. Heat engine convert heat energy to mechanical energy. It will convert heat energy to mechanical energy. Okay, these all are the cyclic process. So, what is the heat engine? There are three system in it. First is source. It is known as the hot reservoir. Second is engine, which is known as the heat engine, and last one is sink, which is known as the cold reservoir. Cold reservoir. Okay. So the heat flow from it Q1, it is at temperature T1. Heat flow from it is T2. Okay. So what will happen? Heat will flow from it. Some work is done on the heat engine. So this work done is defined as by Q1 minus Q2, and the rest amount of heat is supplied to sink to Q2. So efficiency of heat engine can be defined by work done by Q1. So Q1 minus Q2 by Q1. So 1 minus Q2 by Q1. This is known as the efficiency of heat engine. So efficiency of heat engine in a percentage can be defined by 1 minus Q2 upon Q1 into 100. So this is known as the efficiency. But if Q2 equal to 0, if Q2 equal to 0, so what will happen? N percentage is equal to 1 minus 0 into 100. So which will become 100% efficient. But this is the hypothetical condition. Means it is saying that no heat can be extracted. That all heat converted into work done, which violates the Kelvin-Planck's statement. Kelvin-Planck's statement saying that all heat can never be converted into work done, or we cannot find a device which is 100% efficient. 100% efficiency means no heat can be extracted. So all device must all device must be release the heat. Okay, so this is the heat engine. So what is question saying that why heat engine with 100% efficiency can never be released? Because I know I give you an explanation that Q2 equal to 0, so N equal to 1 or 100%. So what happen in this process? The no heat can be extracted, so which will violate Kelvin Planck's statement. So that's why it can never be released in the practice. Now next is in summer when the valve of a bicycle tube is open, the escaping air appears cold. Why? Appears cold. Why? So okay, this is a cycle valve. Air inside it are insulated. In the star of the cycle, air inside it is insulated, so there will be a no exchange of heat. So if there will be a no exchange of heat, they will remain at a cold position. Okay. So when we remove the valve of a bicycle tube in the summer, so that's why it will appear cold, because due to the adiabatic expansion. Due to adiabatic expansion. Due to adiabatic expansion. Next question is your short answer type questions. Next are your short answer type questions. Short answer type questions. Now, first question is state and explain first law of thermodynamics. State and explain first law of thermodynamics. State and explain first law of thermodynamics. Okay. So, what is the first law of thermodynamics? I have discussed in the class in the previous year in the normal revision sessions. See the video of thermodynamics. The first law of thermodynamics is saying that heat supply to the system is equal to the work done plus internal energy of the system. So this is the first law of the thermodynamics, and it is based on the law of conservation of energy. Okay. See the previous class of thermodynamics prior to that. In that class, I have conservation of energy. In that class, I have described about this, the heat supply, first law of thermodynamics in detail. Now, next question is two principal specific heat of a gas and which is greater and why. So, define two principal specific heat of a gas and which is greater or which is lesser. Which is greater or which is lesser, or which is lesser. So the two principal specific heat of gas are specific heat at constant pressure. That means heat supplied to the system equal to number of moles into delta T. Molar specific heat is defined as the heat required to raise the temperature of 1 mole of substance to 1 degree Celsius at constant pressure is known as the molar specific heat. And the value of Cv is heat required heat supplied to the system to raise the temperature of 1 mole of gas to 1 degree Celsius at constant volume. And we know that Cp is greater than Cv. Why? According to according to Mayer's formula, Cp minus Cv is equal to R. So Cp is equal to R plus Cv, and R is universal gas constant. The value of R are 8.314 joule per mole Kelvin or 2 calorie per mole Kelvin. So both are the value of R. So that's why Cp is always greater than Cv. Okay. The next question is derive a relation derive a relation between two specific heat capacities, two specific heat capacities on a gas, on a gas. Okay. So firstly, you can define the what is Cp. Now you can define the Cp and Cv. Now derive the formula of Cv. Cv is defined as the f upon 2 plus 1 times of R, and Cv is defined as the f upon 2 of R. Now if you subtract Cp minus Cv, you will get the value f upon t plus 1 times of R minus f upon 2 of R. Now if you take R common, so f upon 2 plus 1 minus f upon 2. So you will get the value R. So this is the relation between Cp minus Cv. Okay, student. So that's all for today. In next class, I will discuss some more important question related